In this video we study the reliable broadcast problem. Before we define reliable broadcast, let us first consider the basic, best effort broadcast. We are given a distributed system comprising a set of nodes, all of which can interact directly by exchanging messages. Assume that one node is the current sender, that is, this node wants to broadcast a certain message, in the example the value 8, to all other nodes. In the simplest possible broadcast algorithm, the sender simply sends a message containing the value 8 to all other nodes. If all goes well, every node receives the message and the broadcast concludes successfully. However, in practice, there might be failures. There could be simple crash failures where nodes suddenly stop functioning, or Byzantine failures, that is, arbitrary failures including malicious behavior. It is much harder to implement a useful broadcast routine that delivers messages reliably if there can be such failures. But before we can talk about how to solve it, we need to define what we mean by reliable broadcast. A reliable broadcast protocol must have the agreement property. That is, if messages are delivered, they must all be the same message. The second property is called totality. The property says that if a correct node delivers a value, it may take some time but the message is eventually also delivered at all other correct nodes. The third property is the validity property, which says that if the sender is a correct node and it sends some value x, then exactly this value will eventually be delivered at every correct node. What if the sender is faulty? In this case, a message may or may not be delivered but no guarantees can be made. Lastly, the integrity property says that at most one message can be delivered in every protocol execution. In practice, different instances of the protocol are used to deliver multiple messages. Note that the integrity property often includes the requirement that any delivered message must have been broadcast. Since this requirement is often satisfied trivially when the protocol has all other properties, we will not discuss it in this video. There is a famous algorithm, proposed by Gabriel Bracha, that solves the reliable broadcast problem in the asynchronous communication model as long as strictly less than a third of all nodes exhibit Byzantine behavior. The algorithm is quite simple, requiring only 3 rounds of message exchanges, where the first round is initiated by the dedicated sender. While the algorithm's resilience to failures is optimal, there is one important metric where the algorithm is not optimal, and that is its communication complexity. The communication complexity of an algorithm is simply the maximum number of bits that all correct nodes send together in the worst case. So what is the communication complexity of Bracha's algorithm? Given a message m, we use vertical bars around m to denote its size in bits. In the algorithm, every node sends the message to every other node twice, once in an echo message, and once in a vote message, so the communication complexity is roughly 2 times n squared times the size of the message. Since every node needs to receive the message, it is clear that the communication complexity must be at least n times the size of the message. As we can see, the communication complexity of Bracha's algorithm exceeds the lower bound by a factor of n. This looks like a large overhead. So the natural question is, can we do better? As we will see in this video, the answer is yes. However, we need to introduce some powerful tools to get a much better bound. The main tool that we are going to use is erasure coding. In erasure coding, a message is a sequence of so-called symbols. The symbols are encoded into more symbols. The encoding has the property that the message can be recovered even if some symbols are erased. In the example here, we have 7 symbols. Let's assume that any 2 of those symbols are erased. We can run the remaining 5 symbols through a decoder to recover the original symbols, that is the original message. We will now use this technique in a reliable broadcast algorithm. In the first round, before sending any messages, the sender encodes the message using erasure coding, creating exactly n fragments, where n is the number of nodes. Note that the number is 4 in this example. The message itself consists of f+1 symbols, which is 2 in the example. Note that a message of arbitrary size can be used in practice by considering it a sequence of f+1 symbols. Each group of f+1 symbols can then be mapped to n symbols. We keep things simple here and say that the message itself consists of f+1 symbols as mentioned before. So, given a message, the sender encodes it into n fragments. The encoding ensures that any f+1 fragments suffice to reconstruct the message m. The sender then sends one fragment to each of the nodes, including one to itself. We assume that all nodes and fragments are numbered, so it is clear which fragment should go to which node. All nodes store the received fragment. We assume in the example that node 4 immediately crashes. Since the algorithm must be able to handle one node failure, the reliable broadcast should still succeed. In round 2, each node sends the received fragment to all other nodes. Now, let's define the rules of the algorithm. If f+1 fragments are received, which is enough to recover the message, a node decodes the message and then computes all fragments, just like the sender did in the beginning. So, after this step, a node locally stores not only the message M but also all fragments. The second rule says that a node broadcasts its fragment as soon as the node gets it. A node may get the fragment in the first round from the sender directly, or it might get it by encoding the message into fragments once the node has the message. The third and final rule says that a node that receives n-f fragments delivers the message M and terminates. Note that n-f is greater than f+1, so the node must have message M already. This is the entire algorithm. It merely consists of 2 rounds. In the first round, the sender disperses fragments and the nodes broadcast their fragments in the second round. While this sounds easy enough, there is an important complication that needs to be discussed. What happens if the sender is faulty? Note that a malicious sender could send arbitrary data, which is not a valid encoding of a fragment. In the example here, it sends some random data to just one of the correct nodes. In round 2, the malicious sender sends more inconsistent data to all nodes. As we can see here, each node gets 2 different pieces of random data. If they feed this data into the decoder, each node will get a different message. Clearly, if this situation is not prevented, the algorithm cannot have all the properties that we defined in the beginning. How do we ensure that the fragments that nodes receive are actually valid encodings of some message? We are going to use Merkle trees to solve this problem. In a Merkle tree, all pieces of data, in our case, the n fragments, are the leaves of the tree. Each fragment is hashed, producing a list of hashes. Then, pairs of hashes are concatenated and hashed again, creating the next level of hashes. This process is repeated until only one hash, the root hash, remains. If all nodes know the root hash, it is easy to provide a proof that a fragment is consistent with the root hash. For example, if fragment F2 needs to be verified, we can pass along hash H1, H9 and H12. Together with fragment F2, these hashes are enough to recompute the root hash H0. These hashes together are the so-called Merkle proof for fragment F2. So, in our algorithm, instead of just sending fragment F2, the Merkle proof for F2 is sent along. The recipient can then verify that the received fragment is consistent with the known root hash H0. Why would the node know the root hash? A simple solution is to first run Bracha's algorithm to deliver the root hash at all nodes. We are interested here in the scenario where the message is much larger than a hash, so the added communication complexity is small and independent of the message size. Alternatively, agreeing on the root hash can be baked into the reliable broadcast algorithm itself. In the following, we just assume that the root hash is known. What is the additional cost of adding these Merkle proofs to every transmitted fragment? Since one hash is needed at each level of the tree and the number of levels is logarithmic in n, log n hashes must be sent with each fragment. Capital H denotes the size of a hash. Again, assuming that the message is much larger than a hash, we can accept this additional communication complexity. However, we are not out of the woods yet. What if the entire Merkle tree is correct, but the fragments at the leaves are not valid encodings of a message? In this case, all messages are accepted, even though they cannot be meaningfully decoded. Fortunately, there is a simple solution to this problem. Again, we assume that the nodes know the root hash. Once sufficiently many fragments have been received, the node recovers the message. After that, the node encodes the message to get all the fragments. Next, the node recomputes the entire Merkle tree, all the way to the root hash. If this computed root hash matches the expected root hash, then the message and all fragments are valid. If the root hashes do not match, then the entire execution can be aborted without delivering any message. Note that it is infeasible for a malicious sender to cause this hash check to fail at some nodes but succeed at others, so it is safe to abort the execution because no correct node will deliver any message. In the following, we assume that all nodes use this verification mechanism so that it is not possible for Byzantine nodes to cause problems. After this detour, we can now show that the presented algorithm is indeed correct, one property at a time. We will start with the agreement property. Recall that the agreement property says that if correct nodes deliver a message, it must be the same message. Since we said that the nodes agree on the root hash, and since it is infeasible to find different messages that have the same root hash, it follows that correct nodes deliver the same message. Next, we show that totality holds too. If a correct node delivers a message, it must have received at least n-f fragments of that message. Since at most f of those fragments may have come from faulty nodes, every correct node receives at least n-2f fragments, which is at least f plus 1. Recall that f plus 1 fragments are enough to recover the message, so every correct node will eventually have the message. Moreover, every correct node eventually broadcasts its fragment, ensuring that all correct nodes eventually receive fragments for every correct node. Since the number of correct nodes is n-f, all correct nodes eventually deliver the message. The validity property states that the sender's message will be delivered if the sender is correct. We can show that this property holds as follows. The correct sender sends a different fragment to each node. Every correct node broadcasts the received fragment. As there are n-f correct nodes, every correct node eventually receives at least f plus 1 fragments and recovers m. Once every correct node receives n-f fragments, they deliver m and terminate. Lastly, the integrity property holds for the same reason as the agreement property. Since only the message consistent with a specific root hash is accepted, at most one message can be delivered. This concludes our proof. What is the communication complexity of this algorithm? First, we need to determine the size of a fragment. Since k symbols are mapped to n symbols and k is f plus 1, which is about n divided by 3, the size blows up by a factor of 3. This means that the size of a fragment is about 3 times the message size divided by n. Note that the size of the Merkle proof is added here for the sake of completeness. Since every node broadcasts the received fragment, the communication complexity is roughly n squared times the size of a fragment. Plugging in the fragment size, we see that the communication complexity is 3 times n times the message size, plus a term independent of the message size. Let's summarize what we've learned. We discussed the reliable broadcast problem, which requires that a correct reliable broadcast algorithm has 4 properties: agreement, totality, validity, and integrity. In particular, we tried to reduce the communication complexity, that is, the number of bits that all the correct nodes need to send around. To this end, we introduced a few helpful tools, namely erasure coding and Merkle proofs. We discussed an algorithm that uses these tools to reduce the overhead to a factor of 3, which is a significant improvement compared to Bracha's algorithm. Thanks for watching.